Presentation, I want to say something about feed-forward neural networks. So as we have seen last time, what we studied last time were perceptrons, and perceptrons are a single-layer feed-forward network. As we have seen, they work really well for domains which can be linearly separated. We could implement networks for and or and not and others. But they do not work well for things, for functions that cannot be linearly separated. And so the Boolean XOR function was one of them. So in this, we will see that feed-forward networks have hidden layers. They have more than one layer. And they can learn functions that are not linearly separable. So the good news is that most of the concepts for feed-forward networks are the same as for perceptrons. And the key difference is the way in which we determine errors in the non-output layers. So that's really what we need to understand. So let's have a look at the basic architecture of a feed-forward network. Again, we have input units, which are not considered neurons. We just clamp some input data onto it, an input vector. We have the output unit. We may have more than one output unit. Obviously, realistic networks have, well, many of them have more than one output unit, unless you want to have a binary output. And then we have hidden units. And so this is a very simple network. It has 4 hidden units. We may have more than one hidden layer. There are certainly networks with 2 and 3. But beyond that, I'm not sure whether we have networks with more than 2 or 3 hidden layers in the real world. So then we have connections between these units, those directed connections, and those are called the weights. So we have wkj over here, wji over here. So from k to j, j to I. And the weights are really what contain the knowledge of the network. It is obviously a giant weight matrix if it's a giant neural network. And the weights are the only thing that we can change. I mean, as part of training the network, the weights will be adjusted. So you may argue that, well, geez, you know, what happens if I set one of these weights to 0? Then you kind of change the network architecture. I kind of like that's a good way of looking at it. But there are some ways in which people optimize the training of neural networks by sort of like turning off some of the connections, so you don't have to train over this giant weight matrix. And so if the weight matrix is smaller, then the training obviously will be faster. So again, the only difference then are the hidden units, or the hidden layers, and the hidden units and the hidden layers. So let's revisit XOR and so like understand what the hidden layer buys us. So XOR, again, we cannot linearly separate the outputs. We have an output of 0 over here, an output of 0 over here, and then 1 and 1 over here. So how do we do this with a hidden layer? So here is a network that was engineered by Goodfellow and others. The image actually comes from a key book, from a very popular book on speech and language processing by Jurafsky and Martin. So what we want to do is we want to like understand how this hidden layer helps us develop a solution to this thing. I should tell you that these grayed out nodes are bias nodes. We will ignore them here for now, or at least the concept of them we will ignore. But when you run this neural network, which I will ask you to do in a minute, you have to take these into consideration. Basically, a bias node enables us to adjust the threshold of the activation function, left or right, and that comes in handy in cases. Okay, so what I would like you to do is on the site where you got the slides, there's an exercise on XOR, which is exactly this one here. So I'll ask you to please complete this thing, and then when you're done, please come back. So assuming that you did the assignment, let's have a look at what the hidden layer does for us. So what we have over here is we again have the original space on the left side. And then what we do over here is, remember, we had these 2 hidden units, H1 and H2. And based on the exercise, you will not, and then the outputs here are actually the y. That's the output, or the y1 that we're interested in. So notice that we have, as combinations for h1 and h2, we have 0, 0, in which case the output should be 0. We have 2, 1, 2, 1, in which case the output should be 0. And then we have 1, 0, and 1, 0 for the 0, 1 input and the 1, 0 input. And they should be 1. So they both map into this thing. But the key thing is that you can tell that you can linearly separate this thing. So that's what the final output unit does. It enables us to linearly separate these things. So I thought that was a really fascinating way of visualizing what these multi-layer feed-forward networks are doing for you. All right, so, but moving on then. So the network that we have seen in the prior slide was designed by humans, and there are other ways to solve XOR. What we want to do now is we want to study the training algorithm for feed-forward networks. And again, the key aspect here is to determine the error of each unit. So the output unit, calculating the error at the output unit is the same as for perceptrons. We have a value that is being calculated by the network, and we know the desired output. And so we do desired output minus this one over here, and that's our error. Okay? But the challenge is, what's the error of this unit, or this unit, or this unit? We can't so simply do, you know, this output over here minus this one over here. That just doesn't work. In essence, what we will be doing is there's an error that we have over here, right? That is produced by the final unit. And again, many times we have more than one unit, so we have the sum of all the errors. And we can sort of like say, hey, look, you know, we can sum this all up, and that's the overall error of the neural network. And what we'd like to do is we would like to bring down the overall error. And undoubtedly, these units contribute to the overall error. So we want to determine what's the contribution of the overall error of this unit, of this unit, this unit, and this unit. And again, if we have more than one hidden layer, we will continue on like that. So let's have a look at a neural network. So we have the output layer, we have a hidden layer, and by the way, we're going to go backwards here. Output, hidden, and then in the prior example, you know, this was the input layer, but it could be another hidden layer. It doesn't matter. So suppose what we want to do is we want to determine the error of this unit here, the shaded unit 3. Suppose we already calculate the output, the error at the output layer for this unit, this unit, this unit, and this unit. Now we also know that in this particular example, 3 contributes or sends its output to these 4 units. Again, I left out all the other connections. And so as such, undoubtedly this node contributes to this unit's error, this unit's errors, and so on and so forth. So that's what we need to ascertain. Now let's put in the weights, right? I mean, there are weights associated between unit 3 and this output unit 1, and this, and this, and this. And so what we're going to do is we are saying that, okay, this unit here produces a certain error. Let's multiply it with this weight. And that is part of the error of this unit over here. And so what we're going to do is we're going to sum up the product of the errors and the weights, okay, which is what I have over here. So this error times this weight, 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 and that's the error of this unit over here. That's it, okay? Now, when we go down, we'll do the same thing. So this unit over here is connected certainly to that one and probably some other ones. So we now know the error of this one over here. We do the same thing. Weight times error, weight times error. I'm sorry, weight times error, and so on and so forth, wherever this one goes. So that's how we will determine the error of the units at the hidden layers. So notice that we have errors over here that help us adjust these weights, errors over here that help us adjust these weights. Now, what we will do is we'll talk about the backpropagation learning algorithm. So that's a key algorithm, a classic algorithm in neural networks. It has 2 stages, just like with perceptrons. We first run the network on an input to produce an output, just feeding it forward, so to speak. And then we will calculate the errors of the units, and that is being done backwards. So we start with the output layer, Then we go to the hidden layer that's connected to the output layer. Then we go to the hidden layer that's connected to that first hidden layer. So hence, we backpropagate the error through the network until we're at the weights that come from the input units. So let's have a look at a training algorithm, again, sort of from the Russell and Norvig classic book on AI, AI, a Modern Approach. This is from the 2nd edition. So in this example, just like with perceptrons, we have a set of vectors that represent our examples. And so obviously each example has to have some data for all the input units, and then it has to have a sample point for the desired output. So M is a number of layers. The input layer is layer 1. It's not 0 based. So what we're going to do is we pick an example, and then for each node in the input layer, we'll take that corresponding value from the vector of the example and set it to that value. And then again, so L equal 2 is then the first hidden layer. Those are actually units. Just like before, we calculate the input to that unit, and then we run the activation function on it. Okay. What I should tell you is that once we go to multi-layer feed-forward networks, we have at least sigmoid activation functions. So we're kind of moving away from step functions. So we do this for all layers, and we're going to reach some output data. So now let's go to the portion of the algorithm that I explained earlier, like in this slide over here. So let's see whether we can understand that. So what we're going to do is, for each node at the output layer, we calculate the error. Like I said, we look at the actual output and we subtract. We look at the desired output and we subtract the actual output. And so the actual output is this one over here. Now we multiply this thing with G prime of in to that unit. So we'll explain that here in a moment about what we're doing over here. But the key idea is even for perceptrons we do that because, as I said, we now have a sigmoid activation function. That one is differentiable. So the difference of this value here is multiplied with the derivative of the function. In other words, the slope of the activation. That's how you can visualize this thing. So now we have the error for each node at the output unit. So now we have these 3 for loops, and there are other ways of representing this thing. But the idea is we now do something for all the other layers. So notice that in this particular example, we will calculate for the topmost hidden layer the error. Again, we take the weights, like I told you, Sue, and then the output, the error of this unit over here. Okay, so that's what we're going to do. Again, just like we did over here, we'll multiply that with the differentiated value of the input to that unit, which is in essence then producing the output or the slope of the output. And these are the errors. So now what we're going to do is we are going to sort of like go back to layer L+1, which is the first time we run this thing is the output layer. And now we're going to adjust the weights of the output layer. And so why are we doing this in this sort of like teeter-totter fashion? Well, because in order to determine the error, we want to use the old weights. We don't want to use the new weights because that wouldn't be nice. And so that's what we do. It's the same thing as before. It's the learning rate. It is, and it's the error over here. All right. So plus we also multiply in AJ. Leave the presentation for a moment here. I also managed to crash PowerPoint in the process of doing that. So let's go back to this algorithm over here. AJ, that is the same as this one over here. Okay, that is that's the activation, except it is. It's not. It's not. This is the differentiated value of the activation. AJ, look at this, J to I, so it goes from node J to node I. that's the activation of node J. So remember, we're adjusting the weights based on the error, the learning rate, as well as how important is the incoming node's value to us. And so the idea is, if it has a high value, it must be important. So we probably want to adjust the weights more quickly than if it is a low value. So that's kind of like the idea of that one. So here's the entire training algorithm then. Everything together. Again, stopping criteria. We'll talk about those more, or you'll learn more about those in the programming assignment. But the key idea is, we typically want to stop when the overall error gets to be beyond its threshold. But sometimes we simply run the network just for a fixed amount of iterations. Now, I know some of you are probably pretty comfortable with looking at this pseudocode, but if you rather want to think in Java, I have implemented this algorithm in Java, so it's pretty much based on this, on the pseudocode. I explain lots of things, and then the trained network is actually the backpropagation algorithm. So just look at all the comments in here that I have and what we do in all those different spots. Okay. All right. So let's see. There are two concepts that you hear a lot when we talk about neural network trainings. One of them is the loss function, and the other one is gradient descent. There are many different loss functions, and you'll probably explore several of them. Or we certainly will do that as part of looking at more complex neural network architectures. For right now, our loss function is simply the sum of the differences between the desired and actual output. What we want to do is, or what we want to do as part of backpropagation is we want to reduce the error or minimize the loss function. And so in order to do that, we express that in terms of gradient descent. So it's an iterative optimization algorithm for finding a local minimum and a differentiable function. So notice that that's exactly what backpropagation does, is we run this thing many times, and a key aspect of optimizing the weights or changing the weight is the differentiated value of an output of a unit. So that's what we want to do over here. So here's a nice visualization. We want to find a minimum. Ideally, there's only one. All right. So what I want to do next is I want to study a key modern neural network. It's called NetTalk. And so just to give a little bit of background about the way the world sometimes works, Minsky was a very influential AI researcher out of MIT. And so he and Seymour Papert published a book called Perceptrons. And it was published in 1969. And it had the unfortunate effect of bringing research into neural networks to a standstill. So nothing happened really during the 70s and very early 80s. So then in the 80s, some researchers showed some renewed interest in neural networks. And they developed many of the network architectures that we use today. So Terry Sejnowski and Charles Rosenberg developed a neural network system called NetTalk that sort of really demonstrate to people that, wait a minute, these things are actually quite powerful. Maybe we should sort of do some more work on them. And the rest is kind of like history. So it really jump-started research into neural networks. Incidentally, convolutional neural networks, which we'll again study next time, they were developed in the late 80s. So the paper, I think, was published in 89 or 90 or 91. I forgot. We'll see about that. So let's have a look at NetTalk. So NetTalk was, let me make sure I have the right slide, yes. So here's an example that we're going to be talking about, well, a figure from the paper that I also link on our website. So it was trained on English text at the input units and phonemes, i.e. the ways of sounding characters of text at the output. So the way they did that is the input text was presented on a sliding window of 7 characters, 1, 2, 3, 4, 5, 6, 7. And so right now that provides the context. So right now we want to learn how to properly pronounce C in this context. and it's cat, right? So that's why we have the sliding window. Next time around, we'll learn A, and as you may know, that the way we pronounce characters so it depends a little bit on the context. There were each of these 7 units. Each of these 7 groups had 29 units. I suspect it has to do with the number of characters, and then we have like space and full stop and those sorts of things. The hidden layer consisted of 80 units, and the output layer consisted of 26 units, corresponding to 26 phonemes. The network was fully connected. They also did use bias inputs for each of the units, again, to sort of like adjust the threshold one way or other. All right, so what I would like you to do next is I would like you to watch a brief excerpt from the audio recording. Again, I have linked it over here. If that link doesn't work for you, it's also linked on our website. So assuming you did that, as you can tell from the recording, it is pretty amazing. So the thing was first babbling, and eventually I saw it was reading like a child might read. So pretty impressive. Now, again, I mean, you probably already know that, but neural networks need a lot of training. So you have to do it a lot, and the training data has to be reasonable. So Sejnowski and Rosenberg, they picked two training data sets. One of them was phonemic transcriptions from informal continuous speech of a child, and as well as from a 20,000 word corpus of a dictionary. They selected a subset of 1,000 words that sort of represent the most common words in English. So what we will see here eventually is that neural networks are like sponges. They absorb information, or as we will see, patterns in the training data, and they get to be really good. Alrighty, folks, that is it. I'll say a few things about the programming assignment next time. Bye.